During hydrocarbon production, physical and petrophysical properties of a reservoir may change. Similarly, physical properties of hydrocarbon may alter. And for an optimum production, it is very critical to understand the hydrocarbon behavior during production. In this lecture, I'm going to talk about hydrocarbon behavior during production. First of all, just let's review some important terminologies. The first important terminology is standard temperature and pressure. According to the Society of Petroleum Engineers, the standard temperature is 15 degrees Celsius or 59 Fahrenheit, and the standard pressure is 1 bar. Another definition or terminology is hydrocarbon initially in place, which means the volume of hydrocarbon at the reservoir condition. So why this terminology has been defined? Because the volume of the hydrocarbon at the reservoir condition is different from the standard condition. And because when we sell the hydrocarbon, we sell it according to the standard condition, it is very important to understand the change of the volume of the hydrocarbon at the surface facility compared to the reservoir condition. And that is very important when we evaluate the economy of a reservoir. A stock tank oil initially in place, or STOIIP, is another important terminology, and it is the volume of the hydrocarbon at the reservoir condition. And another terminology is gas initially in place, or GIIP. Again, it means that the volume of the gas at the reservoir condition. Now, let me delve into the concept of hydrocarbon in more detail. Hydrocarbon is compounds of carbon and hydrogen, and they can be divided into two major categories. Open change hydrocarbon means that we have carbon-carbon compounds with respect to the hydrogen that are attached to them. Make a chain structure. And they can be saturated or unsaturated. Another type of hydrocarbon or category of hydrocarbon is cyclic or ring structure. That means that carbon-carbon compounds will make a ring structure as you see here. Again, they can be saturated or unsaturated. So the first group of open change hydrocarbon is alkanes, and they are saturated open change hydrocarbon, as you see here: methane, ethane, propane, and butane. Something that you should notice here, from pentane to hydrocarbon with the equation C17H36 are liquid, above which hydrocarbon has like a wax-like property at the standard condition. It is possible that alkanes have some branches. In that case, we call them isomer. As you see here, we have some branch here. And the example is isobutane, as you see here, or isopentane. Open change hydrocarbons may be unsaturated. It means that they may have one carbon-carbon double bond or one carbon-carbon triple bond. And if they have carbon-carbon double bond, they are called olefin. An example is ethylene. Olefins are highly reactive, and if there are some hydrogens in the formation, they tend to react with the hydrogen to get saturated. So as a result, they are rarely found at the surface facility. But it is possible that heavier or bigger chain of olefin may be found at the surface facility. And as I mentioned, when we talk about unsaturated, they may have carbon-carbon triple bond, and they're called acetylene. Similarly, you may notice that acetylene again should be highly reactive, and they are rarely found in the crude oil. So, as I mentioned before, hydrocarbon may have some change or cyclic structure, and again, they can be saturated or unsaturated. The saturated one, for example, is naphthalene, as you see here. And also, the ring structure hydrocarbons may be unsaturated. An example is benzene. Something that is different when we talk about ring structure or cyclic hydrocarbons, you're stable regardless of being saturated or unsaturated. So, for example, benzene is a kind of very highly stable hydrocarbons. Then, ring structure hydrocarbon may have some branches, as you see here. And these are different compounds of hydrocarbon that we may find in the crude oil. Another important definition is API gravity that has been defined by American Petroleum Institute. And I can say that this definition is very crazy, and the reason I'm going to talk about it later. And it is defined by this equation here. Gamma is the specific gravity of hydrocarbon relative to water. So it means that if we measure the density of hydrocarbon over the density of water, it gives gamma. So we know that for water, gamma is 1. For heavy oil, it is equal to 0.93. For regular oil, it is about 0.825. For light oil, it may varies from 0.78 to 0.82 and so on. And it is defined as degree. For example, we may call it the API gravity is 30 degree or 40 degree. Now, just let me ask you this question. So assume that for crude oil, the specific gravity is 0.825, and how much, so that's the question, how much is the API gravity? Yes, the API gravity is 40 degree. Let's talk about different hydrocarbons that we may find in a hydrocarbon reservoir. As you see here, we may find dry gas, wet gas, gas condensate, volatile oil, and black oil. As I mentioned before, API gravity is a kind of crazy definition, and the reason you may see it here. So as you see here, for black oil, API gravity is 40 degree, but when we talk about, for example, for the wet gas, the API gravity ranges from 60 to 70. So it means that the lighter the hydrocarbon is, its API gravity is higher. And that's the reason I think that it's a kind of crazy definition. Now just let's look at each of these hydrocarbons in more detail. So when we talk about dry gas, you may notice that about 96% of dry gas is methane, and the rest are light elements of hydrocarbon. Okay, and that's the reason dry gas is dry gas, because when we bring the dry gas up to the surface facility, we just produce gas, nothing else. But if we look at the wet gas, for the wet gas, about 88 or 89% of wet gas is methane, and 6% is ethane, and 3% propane. But you may see that we may have about 2% of heavier elements of hydrocarbon that at the surface facility, these elements become liquid or become oil. And that's the reason we call it wet gas. So because when we bring the wet gas up to the surface facility, not only we produce gas, but also we produce a little bit of oil as well. And that oil is very expensive and really is very, I can say that, important when we talk about the economy of the wet gas reservoir. Similar to, again, wet gas, we have gas condensate. Again, as you see here, in gas condensate, we much have higher percentage of heavier elements of hydrocarbon. It means that we produce more oil at the surface facility, and that's the thing makes gas condensate so important and so interesting, because not only its production is very easy, but also it produces a lot of oil. So if we have a gas condensate reservoir, not only we can produce a lot of gas, but also a lot of oil at the surface facility. Now just let me look at black oil. So we know that the black oil is liquid, but again, although it is liquid, we see that about 50% of black oil is methane. But that methane is dissolved into the heavier elements of the hydrocarbon, and the entire system is liquid. The entire phase is liquid, but it doesn't mean that when we talk about black oil, it has no methane. So it has about 50% of methane, 5% of ethane, and 3.5% of propane. Now let's go back to the topic of this lecture, the behavior of hydrocarbon during production. During production, we deal with two important properties. One of them is the reservoir temperature, and another is the reservoir pressure, or the fluid pressure. The reservoir temperature can be assumed to be constant because it is supplied by geothermal energy, and that remains constant during the production. But the major property that changes during the production is the fluid pressure. So when we extract more hydrocarbon from the reservoir, the pressure of the reservoir decreases, and that may cause some change not only in the physical property of the hydrocarbon, but also the phase of the hydrocarbon as well. So it is important to understand how hydrocarbon behaves when the pressure of the reservoir decreases during the production. And why it is important? Because if we are able to somehow understand the behavior of hydrocarbon, as I mentioned before, we are able to plan the best strategies for optimum production. Here I mentioned that one of the things that changes during production is the phase of hydrocarbon. We know that when we talk about the phase of material, the phase can be liquid, can be solid, can be gas. So we have a clear understanding of the concept of phase. Scientists usually use PVT diagram in order to describe the phase behavior when temperature or pressure change. So for example, what you see here is pressure temperature diagram for water. And here you see three regions. This region is solid, this region is liquid, and this region is vapor. And if you're given, the usefulness of this chart is that if you're given temperature and pressure, for example, assume that this is the pressure and this is the temperature, you can easily predict the state of the phase. For example, if the intersection falls here, you may easily say that the phase is solid. And then similarly, by looking at this chart, you're able to somehow predict the state of the phase when pressure or temperature change. Like here, for example, the initial pressure is P0, and assume that the pressure remains constant during an experiment, and something that you change is just the temperature. So if assume that the initial phase is solid because the temperature is low, temperature is here, and the pressure is high, and you see that the initial phase is solid, and then you gradually increase the temperature. Again, the pressure remains constant during the experiment. And finally, at some temperature like B, you may notice a phase change. It means that the solid becomes liquid. And if you keep increasing the temperature, finally at some point, or temperatures such as CC, you're going to notice that the water becomes gas or vapor. Similarly, if you repeat the experiment at much lower pressure, such as P1, it is possible that you may see the phase change directly from the solid to gas. We haven't seen such a thing in our daily life, because in our daily life we have noticed that, so when we heat a piece of ice, it becomes liquid first, and then it becomes vapor or a steam. But as you see here, if we have very, very low pressure, much lower than 1 bar, and if we repeat that experiment at that low pressure, what we're going to notice there is that at some temperature such as C prime, the solid or the ice becomes directly steam or vapor. And here you may notice another interesting point. Here is triple point. Triple point is a temperature and pressure at which we may see the three phase at the same time. And another important definition is critical point. Critical temperature or pressure is high temperature and pressure at which it is very hard to determine the state of the phase, because the fluid exhibits some liquid and also gas properties at the same time. So that's the definition of critical temperature and pressure. Here I'm going to explain how we may obtain temperature pressure diagram for hydrocarbon through an experiment. So here assume that we have just one element of hydrocarbon, such as propane. And what we do here, we fill a cylinder with propane. And then what we do here, as you see here, this cylinder has a piston that by pushing the piston or pulling out the piston, we are able to change the pressure within the cell. And this piston is equipped with a pressure gauge in order to measure the pressure. However, this piston is connected to a pool of water with some constant temperature. So it means that the temperature during the experiment doesn't change. And what we do here, just we have constant temperature during the experiment, and the only thing that varies is the pressure. So assume that in the beginning of the experiment, we push the piston inward as much as we can, and finally we notice that the propane becomes liquid. Okay, so if we measure the initial pressure here, we may notice here that all hydrocarbon that we have within the cell is liquid, the phase is liquid, and then we gradually start pulling out the piston. And at the same time, what we do here, we measure the pressure. So if we continue pulling out the piston, finally at some pressure, as you see here, we're going to see some bubble of gas within the piston. So it means that some gas is liberated from the liquid, and that pressure is called bubble point pressure. So if we keep pulling out the piston, we may we may notice that the pressure doesn't change because, once liquid becomes gas, it expands and somehow it mitigates the pressure drop as a result of pulling out the piston. But finally, we're going to get to some point, as you see here, it's called dew point line, after which the phase is gas. And because right now all liquid has become gas, again, if we pull out the piston further, we're going to notice that the pressure declines. But here, if we compare the pressure decline before and after the phase change, you see that after the phase change, the pressure decline is much smoother. And the reason, because gas has higher compressibility compared to liquid, and as a result, it is more resistant to change in the pressure. Now, assume that we repeat the experiment at another temperature. So in other words, now we change the temperature of the experiment. In the previous experiment, the initial pressure was Ti. Now assume that we repeat the experiment at T1, and as you see here, T1 is smaller than Ti. And if we repeat the experiment, you may notice here that we have to pull out the piston further to see the first bubble of gas. In other words, the bubble point pressure decreases at lower temperature, and similarly, we're going to see that after pulling out piston enough, we're going to get the dew point line. If we repeat this experiment at T2, and as you see here, T2 is greater than Ti, in such a case, you may notice that we're going to get the bubble point pressure at higher pressure, and similarly, we get the dew point line faster. So now assume that we repeat the experiments for different temperatures and pressures, T1, T2, T3, T4, T5, T6, and also at the same time we record the corresponding bubble point pressures that we obtained or we observed during the experiment. And if we plot the temperature versus pressure, these temperatures versus the corresponding bubble point pressures, we're going to obtain a very single curve or simple curve that determines the pressure temperature behavior of the hydrocarbon for that specific element. So again, if we have just single element of hydrocarbon, the pressure temperature diagram is a simple curve. And for example, here, if the temperature and pressure is here, we may easily say that here is liquid. And below this line, if the intersection falls below this line, we can say that the phase is gas. So now assume that in hypothetical situation, just we deal with a propane gas reservoir, and assume that we start producing gas and the initial pressure of the reservoir is here, and we produce gas from the reservoir. So as you see here in the beginning, the phase is liquid, but once we get to this point, we're going to get to the bubble point pressure, below which the hydrocarbon within the reservoir becomes gas. So this is if we have such a diagram, temperature pressure diagram for a specific hydrocarbon, then we are able to predict how the behavior of hydrocarbon changes during the production. But as I mentioned before, when we talk about hydrocarbon never ever is a single element. We have a mixture of different hydrocarbon elements. And when we have mixture of hydrocarbon or mixture of several hydrocarbons, the behavior of hydrocarbon or the behavior of temperature pressure diagram is so complex. So what you see here shows the pressure temperature diagram when we have two elements. So one of them, as you see, is ethane, another is a heptane. And what you see here, you see different mixture of ethane and heptane in this diagram. The red curve is for pure ethane, and the blue curve here is for pure heptane. So as you see, if we have pure ethane or pure heptane, then we're going to end up very simple curve. But here you see that once we change the percentage of heptane and neptane, for example, assume that in the first mixture we have 90% ethane and 10% of heptane. In such a case, the temperature pressure diagram will be a curve like this. Just let me highlight it for you. So what I'm highlighting here is the pressure temperature diagram when we have 90% ethane and 10% heptane. Similarly, if we have 50% ethane and 50% heptane, the pressure temperature diagram will be a curve like this. And finally, if we have 10% ethane and 10%, if we have 10% ethane and 90% heptane, the pressure temperature diagram will be something like this. So as you see, this curve is not that simple, and as a result, interpretation is a little bit more complex. Let's look at the pressure temperature diagram for the case that we have 10% of ethane and 90% of heptane. And I'm going to explain the behavior of the hydrocarbon during production. So assume that the initial pressure of the reservoir is A and A is above the bubble point pressure. It means that here we have pure liquid. Here we have below the dew point line or curve, we have pure gas, and in between we have liquid plus gas. So if the initial pressure of the hydrocarbon is A, so it means that we have pure liquid within the reservoir. Okay, so this is something that we have in the beginning of the production. And I mentioned before that all the process within the reservoir can be assumed to be isothermal, or the temperature doesn't change during the production. So as you see, so if we want to predict the behavior of hydrocarbon, the only thing that we should consider here is the change of the pressure. So once we start producing oil or hydrocarbon from the reservoir, as you see here, the pressure decreases finally to get to bubble point pressure, at which we're going to notice the first bubble of gas within the reservoir. So the first bubble of gas will be liberated from the hydrocarbon within the reservoir. So in the reservoir, we're going to see some liquid and some gas. So if we keep producing hydrocarbon from the reservoir, the pressure will decrease further. And something that I should say here, once the pressure decreases, the first lighter elements of hydrocarbon become gas. For this example, ethane first becomes gas, but once we keep reducing the pressure of the reservoir, heavier elements also go through phase change, and as a result, more heptane molecules become gas. So finally, we're going to get to some point such as pressure C. Below that, we're going to have pure gas in the reservoir. So you see that why the pressure temperature diagram is so interesting, because it can help us to have some idea about the behavior of hydrocarbon during production. And as I said, it is very critical to understand such behavior when we want to design the best strategy for optimum production. So as I mentioned, when we talk about real hydrocarbon is very complex. So actually, the pressure temperature diagram for real hydrocarbon is going to be something like what you see here. Here you see three different regions. The first region that is indicated by blue color is the liquid. Another region, as you see here, that is indicated by yellow color is gas zone. And the white zone is liquid plus gas. Now just let me talk about different hydrocarbon reservoirs that we may find in the nature, and how we should expect about the behavior of the hydrocarbon during the production with respect to, for example, dry gas, gas condensate, black. Now let's look at different reservoirs that we may see in the nature. As you see here, the first type of reservoir that we are talking about is dry or wet gas reservoir. So for dry and wet gas reservoir, as we see here, the temperature is very high, is much higher than Curie-Condon temperature, and Curie-Condon temperature is a temperature above which the phase is always liquid. Doesn't matter how much we reduce the pressure. So it means that doesn't matter how much the pressure of the reservoir decreases during the production, the phase remains always gas. And that's the thing makes a production very easy. So when we deal with dry or wet gas reservoir, it means that we deal with phase gas within the reservoir during the production, and that makes the production very easy. Now, when we talk about black oil or volatile oil or light oil, as you see here is the initial pressure of the reservoir is above the bubble point pressure. In that case, we're going to have pure liquid within the reservoir. But once we start producing oil from the reservoir, we're going to see that at bubble point pressure, we're going to see a fraction of the gas will be liberated within the reservoir. And if we continue production and the pressure at the reservoir decreases, you may notice that more fraction of the oil becomes gas. So in other words, some gas or some light elements that were dissolved within the oil are liberated because the pressure decreases. So as you see here, for example, at this pressure, we're going to have 75% of liquid and 25% of gas. At this pressure, we're going to have 50-50. I mentioned why it is important and why it can help us to somehow to plan the best possible production strategy. The reason because that once the first bubble of gas are liberated from the oil, they migrate to the apex of the reservoir and they initiate a gas gap. And indeed, the gas gap is a good thing for a hydrocarbon reservoir, for an oil reservoir, because somehow gas gap helps for the reservoir to maintain its pressure. So in other words, gas gap will somehow mitigate or prevent further decline of the pressure in the reservoir. So it doesn't mean that it's gonna stop it, but at least when we have gas gap, the pressure reduction becomes slower. And that really helps for production. But here is the thing. Here is a caveat. And the thing is that we don't want oil in the reservoir loses a lot of its gas. And the reason, because once the oil loses its gas, it becomes more viscous, because gas indeed decreases the viscosity of the oil. So once the oil loses its gas, it becomes more viscous, and more viscous oil is harder to produce. So that's the thing. Sometimes, although we like to have a gas gap at the apex of the reservoir, at the same time, we don't want the oil to lose its gas significantly, so it becomes highly viscous and hard to produce. In such a case, we may inject some gas into the reservoir in order to help keep the pressure of the reservoir high and somehow prevent further liberation of the gas from the reservoir. For the volatile oil or light oil, as you see here, this is similar to the black oil, but volatile oil, usually the temperature is high, is close to the critical pressure and temperature. But the most interesting thing, as you see here, is gas condensate. I mentioned before that gas condensate reservoir, the initial phase is gas, and once we bring gas up to the surface facility, not only we are going to produce some gas, but also some oil, and the fraction of the oil is considerable compared to the wet gas reservoirs. But as you see here, for gas condensate reservoir, the temperature is between critical pressure and temperature and critical condensate temperature. So it means that the temperature of gas condensate reservoirs is very high, but it is below the critical condensate temperature. And that gives very interesting behavior to gas condensate. So as you see here, the initial phase of the gas condensate reservoir is gas. But once we start producing gas from the reservoir, finally we're going to get to some dew point pressure, after which, as you see here, a fraction of gas will become liquid and condensate within the reservoir. Something that you should notice here, always producing liquid from a reservoir is much harder than producing gas from a reservoir, because gas has much higher mobility compared to the oil. In addition, once oil condensate within the reservoir, it can block some of the pores and hence reduces the overall permeability of the reservoir. So it is something that we don't want. So if we deal with gas condensate reservoir, the best strategy, the best optimum strategy for production is to make sure that the pressure of the reservoir is always above the dew point pressure. And how we are able to do that is that once we produce gas at the surface facility, we re-inject or recycle gas into the reservoir to make sure that the pressure of the reservoir remains high, doesn't matter how much we produce from that reservoir. So gas recycling is one of the best approaches that we should do in order to reach the optimum production from a gas condensate reservoir. One question that you may ask here is that how we are able to do some PTV analysis or to develop a pressure temperature diagram for a specific hydrocarbon. Something that we do always is fluid sampling from the reservoir. As you see here is a sample chamber that has two aperture, and what we do, we send the sample very close to the production zone, and once we make sure that the entire sample is filled by hydrocarbon, these two aperture will be closed suddenly and the sample is brought up to the surface and is taken to the lab. So in the lab you are able to simulate the temperature and pressure of the reservoir using the lab equipment that we have, and then at the same time we measure the phase gradually reduce the pressure, so we are able to somehow develop a pressure temperature diagram for a specific hydrocarbon. I hope that you have enjoyed this lecture. Through this lecture, you learned that one of the most interesting tools that we may use in order to somehow predict the behavior of hydrocarbon during production is temperature pressure diagram or pressure temperature diagram. And using this diagram, we are able to predict, okay, if right now we have gas in the reservoir, or we have oil, or we have combination of gas and oil, and how to go through the next steps of production by the knowledge that we gain from pressure temperature diagrams. Thank you very much for your attention.